Today we're going to start off by talking about posterior and prior predictive checking. So generative probability models, what are they? A fully specified Bayesian model is called generative. Fully specified means that all parameters have proper priors, all data have a specified likelihood, and any missing data have a generative model. Proper prior, which we talked about last week, means that the prior integrates to 1 over some domain, and generative means that it can simulate new observations. So the idea is that we can compare simulated observations to real observations or to our expectations given our prior understanding of the world. And if the properties of simulated observations are indistinguishable from the properties of the real data, we can gain confidence that we have described the important structure and uncertainties in our system. Putting it simply, if you mixed your real data with several simulated datasets, and you didn't tell someone which was which, they shouldn't be able to slice and dice or visualize the datasets any reasonable way to figure out which one was the real dataset. And the goal is to convince yourself of this and convince any readers of your analysis of this. If you can distinguish your simulated data from the real data, you can then learn from the differences and revise your model. Importantly, there's no wrong predictive check, but some predictive checks are just more useful than others, and we'll see some examples of this throughout. And you might need to get creative with your checking. So there are both prior and posterior predictive simulation checks. Prior predictive simulations simulate only from the priors and ignore the data, and posterior predictive checks simulate new observations based on the model fitted to the data. Within prior predictive simulation types, sometimes they are split up into two types. So you have prior push-forward simulations, which simulate only the expectations from the priors, and prior predictive simulations, which simulate new observations from the priors. We'll see some examples of these shortly. Some people use prior predictive simulations for both of these. So weakly informative priors, which we talked about last week, in this paper on visualization of Bayesian workflow, they have this great quote that we say that a prior leads to a weakly informative joint prior data generating process if draws from the prior data generating distribution, Py, the probability of y or observations, could represent any dataset that could plausibly be observed. So for weakly informative priors, we want some probability of extreme but plausible datasets and virtually no probability of completely implausible datasets. And so we can check our priors for these properties. This is an example of that at the beginning of that paper on visualization in Bayesian workflow. This is looking at observed log of air pollution, a certain size, PM 2.5 size. So on the y-axis here, we have simulated data, and on the x-axis, we have the observations of the air pollution. And on the leftmost panel, we have an example with vague priors. Middle, we have an example with weakly informative priors. And on the right, we have those same simulated datasets overlaid on the same axes to look at the difference in scale. And so the point here is that on the x-axis, where the real data are observed, they range roughly from 1 to 5. And if we went into this with some domain knowledge, we would probably know the possible values of this particular matter. And on the y-axis, where we have simulated data, if the vague priors are used, we have this really wide range in the simulated observations. It goes all the way from 200 to 800, which is really different than the observations. With the weakly informative priors in the middle, we end up with a smaller range of the simulated data that still is wider than the observations, but it's not dramatically wider. And they make the point in this paper that you can make a flipbook of simulated data sets with all sorts of different priors to understand the properties and the implications of different priors and come up with weakly informative priors for all your parameters. So that was an example of prior predictive checking where we are simulating new observations, and the other type we talked about was a prior push-forward simulation. This is an example from a recent paper by Cole Monahan and Fisheries Research, which is thinking about how to apply those Bayesian workflow ideas to stock assessment. And in this example, he is plotting length against age for a specific fish. The posterior is shown in red, and it's quite thin because it's very small in range compared to the variability across the different prior draws. And the blue are draws from the joint prior, the prior across all the parameters in the model. And so on the left, we have a broad uniform prior. We end up with a really wide range of length-age relationships. Then we have some informative priors that are based on meta-analyses in the R package fish life, one based on class level and the next one based on genus level information. And those get both tighter and more reflective of our expectation for what the relationship could look like, as we see by overplotting the posterior. So importantly, these are performance simulations because we're looking at the expectation of length against age. We're not looking at the length of individual fish on the y-axis, which would be a prior predictive check. So we're looking at the mean relationship between length and age. And this is an example where I think for a lot of people, they've probably seen a lot of length-age relationships, and they may find it more intuitive to gauge the reasonableness of given prior values by looking at the curve here as opposed to looking at a scatter plot of length against age. But both of them are valid. So there are many approaches to predictive checking. I think you could probably group them into these three. You've got visual checks. What we've seen so far is just purely visual. There's visualization of statistics, and we'll show some examples. And then there's purely statistical. My preference, and I think Gelman and et al.'s and everyone in the STAN community generally prefers these visual checks, but there's also statistical ones. So visual checks, this is probably the most common visual check, and it's really the default that's used in a lot of packages. And that's just looking at the density of the observations against simulated values. So it's a smooth, basically a smooth histogram of the observations. So the singular kind of thicker solid lines, those are the observations themselves, the real data. And then the thin lines behind are multiple replicates of draws from the posterior predictive distribution, so the distribution of simulated observations across 50 or 100 or so of them. And so in model 1, we can see there's quite a divergence between the simulated values and the observed values. So we say it looks like it's not coming from the same generative model. But then in model 2 and model 3, the observations, I think, could plausibly be coming from the same generative model because they really overlap each other. So sometimes we need to get creative with posterior predictive checks in order to see problems with our simulations. So this is an example here. This is from what used to be on the cover of the Bayesian data analysis book. And you've got data for some metric that I forget at the moment, but it's across 6 individuals. So the rows here are different individuals. And the leftmost column, these are the actual observations. And then this sort of rectangle on the right, these are 7 posterior predictive simulations. So each column is another replicate that is simulated from the model. And in this case, if you just plotted them out with a random ordering of the various metrics on the x-axis, it's hard to tell. You might think that they actually resemble each other. But in this case, if you order the metrics left to right, order the data points by some value, you can start to see that there is clumping in the observed data on the left that you don't see in the simulated data. So by this creative visualization, you can see that there are aspects of the observed data that are not captured through the generated simulated data. And we ideally would want to include those in our model. So visualization of statistics might look something like this. You calculate something here, skewness, and you calculate it on both your observations, and you calculate it over and over on the simulated draws from the posterior. So the distribution of doing that across a whole set of simulated draws is what's shown in the histogram, and the observations are the vertical line. So in model 1, there's much more skewness in the observed data compared to the simulated data. Model 2 is starting to overlap, but it's a fairly unlikely value because it's towards the edge of the histogram. And model 3, the observed skewness is right in the middle of the simulated skewness distribution. So the statistical posterior predictive checking is often in the form of something called Bayesian p-values. And in a Bayesian context, a posterior p-value is the probability given the data that a future observation is more extreme as measured by some test variable than the data. And so we can calculate that and report those p-values for our model. And this scales well, say, to lots of things you want to look at, lots of parameters, but you can't necessarily capture some of the harder to quantify aspects of the way that a model is not representing the data. So generally, it's useful to look at visualizations of something like this or like this, where you can capture aspects of the data that you can't necessarily quantify in any single statistical metric. So now we're going to open up file 06 posterior predictive, and we're going to go through some exercises where we are going to do posterior predictive simulation checking in order to find problems with our model. And in each case, I have simulated some data in a data frame DF. If we look at this data frame here, in this case, we've got a predictor X and some observations Y. And then I have a matrix Y rep. And Y rep has 100 columns, and that corresponds to the 100 observations in our original data frame that we fit. And there are 20 rows corresponding to 20 simulations from the posterior. So I'm going to make some plots of this. I'm going to extract my observations into a variable y. And then there are several functions for posterior predictive checking, all starting with PPC for posterior predictive check in Bayes plot package. And they all start with that, followed by an underscore, and then they have a function name. So this first one, density overlay, is a very common one, and we saw this in the slides. So this is just a description of the distribution of the response, the observations, sort of a continuous version of a histogram. And in the darker solid line, we've got y, which are our actual observations. And then in the lighter blue, we have y rep, which are our simulated values. So here we can see that it seems unlikely that our observations come from the same generative model because there are some differences here. We've got the tails look a bit different here. It's a little bit skewed over to the right. Something is off, but it's not really obvious what's off at this point. So we have to get more creative and make some other types of plots. So here I am using error scatter average versus x. So this is taking the average of y minus y rep on the y-axis, and then my predictor dfx as the third argument is on the x-axis. And so we would hope that these would sort of be scattered around a straight line, but they're not. So we're seeing there's some curvature here, which is suggesting there's something off. I could use this PPC underscore intervals function. In this case, the observations are the dots, and then the distribution of our simulation replicates is shown in the background with these dots and lines. So I think we have the mean and then some, I assume, 50 and maybe 90 or 95% credible intervals. I'd have to look at the help in the background from the simulated data. And so, for example, here, if we look off into the high and low values of x, our simulated values are sort of they're all following the straight line. And these observations are falling far outside the distribution of those simulated values. So something's off. If we plot here, I'm just going to plot out the observed data in the first panel, and then I'm just picking the second and third simulation replicates here, and we can start to see what's gone wrong. So there's some curvature here, but our simulated data does not have that. So basically what's happened is we have a curved relationship between y and x in our observations, but we have fit a linear regression that is not a quadratic shape. And so our simulated data is following a linear line with more observation error to try and fit these data. and our observations have this curvature. So we fit a linear model to a response that has a curved shape to it with respect to x. And we can see that by looking at our simulated data. Let's look at the second example here. So again, I have x and y. And again, I have 20 by 100 replicates, column for each row of data. I've got 20 replicates. I'm going to make a similar plot of the observed data followed by 2 simulation replicates. And one thing we see here is that we have count data, and we can check that in our observed data as well. It's also counts, even though it's harder to see in this plot. Starts at 0, is in integers, and we do have counts in our simulated data, but it does look different. And I'd say there's 2 things that sort of look different here. You've got more zeros in your observed data, and you've got much more dispersion, much more spread or variance in the data in the observations. We could also look at the density overlay, and you can get the same information in a different way. So there's a lot more low values and a lot more high values. And so what has happened here is we have data that were simulated from a negative binomial distribution. I think it was a NB2 or negative binomial 2, which means that the variance grows quadratically with the mean, whereas the model that was fitted had a Poisson observation and a log link. And the Poisson has a 1-to-1 variance to mean relationship, so the variance cannot grow with the mean nearly as quickly as it does in the negative binomial, and so we don't have enough variance in our observations. Let's look at the third. In this case, I have x, y, and g, which is, if we look at the unique values of g, I've got 5 different levels, and you can ignore yrep2 here. And then I've got some replicate values. So let's try plotting out the data. So the data are in the first panel. I've got 2 simulation replicates here. And you might start to see something is wrong, but it's kind of hard to figure out exactly what is wrong at this point. But you see some clumping in the first panel that you don't see in the subsequent panels. And if I had just done a simple density overlay, I might look at this and say, yeah, it's not too bad, and move on. But what I need to do is plot it against something that I know exists, but was, in this case, wasn't in the model, and that's this G or grouping column. So now I've got my density overlay split by those 5 different levels of the variable G. Some of them look okay, 4 and 3 look okay, but 1, 2, and 5 look pretty far off. So one way to make this sort of obvious, I'm going to make a little ggplot here. I'm going to save the first simulation replicate into a new column in my data frame so that I can plot it easily with ggplot. And then this is what the observations looked like. So that's plotting the actual observations, and you can see that there's grouping here in the colors. But then this is what my simulation looks like. So here's a total scatter shot, whereas the observations don't have that. And so what's happening is I have fit a linear regression to data that actually should have random intercepts or factors for the different levels of G to have different intercepts. But there is a different mean expectation for the different levels of G, and potentially different variance as well. But there's a grouping structure that's missing there. And we can see that through this posterior predictive simulation. Let's open up 05 BRMS Basic. We're going to work through a really simple example, a quadratic linear regression with the R package BRMS. So you might have heard of BRMS before. It's an R package that takes formulas, arguments that you might have seen with GLM or LME4 or MGCV, and it creates stand code, and then it runs the stand code, samples from the model, and has all sorts of utilities to work with the output. So we're going to start by loading our libraries. We're going to set an arbitrary ggplot theme. I'm going to create a folder named cache that I'm going to cache my model fits in. This is just to speed up running this code for me while I'm teaching here. In particular, there is an option for brms.file_refit, which I'm going to set to onChange so that my models will only be refit if I change any of the code in my call to brms. So this is just part of how the caching is set up. Ordinarily, if I was fitting a more complicated model and I wanted to fit my chains in parallel, I could set options mc.cores equals parallel detect cores. And in fact, you'll get that if you want to copy that into your code anytime you load rstan. I'll just do library rstan here. And you can see in the messages that it prints out. For multi-core CPU, we recommend calling this. So I would just copy this in. In this case, I'm not going to call that because this is a really simple model. And in fact, it would probably be slower in this case to spawn those multiple cores than it would be just to fit them all at once. But for models of greater complexity, that can make a lot of sense. So we're going to work with data from this paper that Brent Hughes led, published in Global Change Biology back in 2018. The data come from a mesocosm experiment that Brent ran where he had manipulated water pH and looked at whether or not nutrients and in the experiment, he changed whether or not nutrients were added to represent nutrient loads into eelgrass beds in 14 200-liter barrels. He measured several variables, but the response variable we're going to be working with is increase in mass of sea hares, which is a type of sea slug, after 24 days. And we can look at what those look like. This is what the sea hares look like. So we're going to read in the data, and we're going to filter off just for the variable of interest in this case using dplyr. Using dplyr, we're going to rename the value column to something more meaningful here, and we're going to remove several columns that we're not going to use. We're going to save that to D. So in the end, we have this simple data frame. We have pH, we have nutrients, and nutrients is 0, 1, and then we have our response, which is the change in sea hare mass in grams, free weight grams. We can plot our data. So it looks something like this. We have a bit of a curvature with respect to pH, and there's a bit of a difference probably in the mean between nutrients or no nutrients. So the first thing I'm going to do here is I'm going to rescale. In this case, center by subtracting the mean and dividing by the standard deviation of my predictor pH. This isn't essential, but it helps for several reasons here. One is that it helps us think about priors because it means that we're thinking in terms of units of standard deviation of our predictor instead of whatever arbitrary units we happen to have our predictor in. So we know that the scale is going to be not too much bigger than 0 or 1, somewhere in that scale. It also helps with the quadratic shape that we're going to fit because it means that when we put our predictor into our quadratic linear regression, it means that one variable can correspond to the overall slope and the other one to the curvature, as opposed to having both those things mixed up in both coefficients. It also can help with sampling in STAN if our coefficients are not way too big or way too small, and so working in units of standard deviation can help with that. And afterwards, we can always back transform if we want to the original scale. So we could do that by hand. There's also this built-in scale function in R, and then I'm going to use as.numeric just to strip off some of the attributes that scale leaves. Scale leaves attributes about the initial standard deviation and mean so that you can back transform, but that also can wreak havoc with various model fitting packages. So now I have an additional column, which is pH scaled. And if we make the same plot, but we show pH scaled, on the x-axis, we get something like this. So now this is one standard deviation increase in pH, and this is one standard deviation decrease in pH. And everything else is the same. The mean of the original data is now 0. So to fit a model with BRMS, there's a function in BRMS called BR, for Bayesian regression modeling. And to that, we pass it a formula, just like we would for a linear regression or GLM in R. I'm going to work with the log of this change in mass on the y-axis as my response. There's an implicit intercept. Then I'm going to have pH scaled and pH scaled caret 2. And I have to wrap that in I, and that just protects it, so this literally means pH scale squared. If I didn't have that, this is syntax in our formula for generating interactions, but that's not what I want to do here. That doesn't make any sense. So I need to wrap it in I. And I could have done this similarly with the poly function, particular poly pH scaled, and then raw equals true wouldn't do any internal scaling again to make them orthogonal. I'm going to write them out like this so it's really explicit what we are doing. I'm going to pass the data to the data argument. Because we're now talking about MCMC sampling as opposed to what you might be used to with LM or GLM, we have to specify, or we can use the defaults, but the defaults and what we were specifying is to have 2,000 iterations across 4 chains. And if you look at the help for BRM, which is quite extensive, you will also see that the warm-up default argument is the floor, so rounding down, of iterations divided by 2. So by default, and what's going to happen here, the first 1,000 iterations of each chain are going to be discarded as warm-up, while the no U-turn sampler is being adapted, and then we will record samples after those 1,000 for each chain. I'm telling it here that I want to create a cache of this model in that folder, so if I don't change anything, I can rerun this chunk of code, and I won't have to wait for it to recompile and fit. And then I have to set priors. We're going to talk more about these priors later, but for now, know that there are multiple ways that I can specify priors in BRMS. I'm using the set prior with the character representation of the density. There are other options. There's some examples here. For example, there's this other option using the prior argument and then a non-standard evaluation version of a distribution. So this basically gets interpreted internally as being as character as needed. There's a version there with tilde, and what we're using is the prior string version, really. So for each of these priors, we also need to tell it which parts of the model each one corresponds to, and we're going to come back to this after, and I'll show you how you can figure out what the names of the different parts are. But for now, know that this, class B, are all the beta, or the B coefficients, so that's for my pH scale squared, and my nutrients. I have another prior for the intercept, and I have a prior here on the standard deviation observation error. And that one is a student T with a 3 degrees of freedom, and it's implicitly a half student T because the sigma parameter only has support 0 and larger. So I put those into a vector, and that creates this, which gets passed into BRM. If I fit that, if you're fitting that yourself, you're going to have to wait probably 30 seconds or so for it to compile, and then you'll have to wait a second or two while it fits. But I already have it cached on my computer. If I run summary on my fit, that's the same thing as just typing the model object or running, which runs print fit. The object out of BRM is of class S3 class BRMS fit. So that means when I call summary on that object, it's actually calling summary.brms fit. So if I wanted to get help on that function, I would have to type that, and then I can read the help function. So let's take a look at the output and make sure we understand everything that's there. So first of all, what does the estimate column represent here? Well, if you read the help file, you'll see that the default is the mean is used as a central tendency. So when we look at this, we're seeing this is the mean of the posterior for the pH scaled coefficient. And the documentation will tell you that the s.error is by default the standard deviation of that posterior distribution. And if we had set robust equals true, instead this would be the median and the median absolute deviation, the MAD. So sigma here is our observation error standard deviation, and this is the mean of the posterior of that parameter and the standard deviation of it, which is effectively equivalent to the standard error that you're used to seeing. So because these are stochastic MCMC chains, we need to look at R hat and effective sample size, which we talked about last week, to determine whether or not our chains are consistent with convergence. And we will also do visual checks shortly. But for now, looking at the R hat, our R hats round down to 1.00, which is fantastic. And our bulk and tail effective sample sizes are in the thousands, which is great. We had 4 chains with 1,000 samples each retained. So if they were uncorrelated, we would expect around 4,000. In some cases, because of the idiosyncrasies of how this is calculated, we actually have slightly more than 4,000. But in general, there's not very much autocorrelation in our samples because our effective sample sizes are nearly the same as our number of samples themselves. So if we wanted to get medians, we would set robust equal true. If we set priors equals true in our summary, then we would also get the priors written out here at the beginning. And if we wanted to return something other than 95% credible intervals, there is a probability argument. So its defaults to 0.95. We could change that to 0.87 or 0.89, which McElrath in statistical rethinking advocates for, just because it's different than 0.95 and makes people stop and think, and it's a prime number. So we could change that. You might change it to 50%, 80%, 90%. As that gets closer to 1, these values are going to get more unstable because these are calculated off of the stochastic MCMC samples. So until you have a ton of samples, these are going to get less stable as you get more and more out into the tails of the posterior. Just something to think about. So I mentioned before not knowing what priors were. Well, we're going to look at the next exercise about how to get them out before we fit the model. But if we fit a model and we want to get the prior summary out of our model, we can call prior underscore summary on our fit, and we get this data frame. I'll pull this over here so this is all on one line. So this is saying that our general prior for any B or beta coefficient, any fixed effect in our model, has a normal 0.5 prior. We didn't specify individual priors for the different coefficients, although we could have through the coef argument in those priors. So they all got the same prior of the 0.5. And then our intercept had this prior, and our half student t degrees of freedom 3 prior on our sigma. Group would be used here if we had, say, groups in random effects. I can't off the top of my head remember what RESP is. I assume response. This is a dispersion parameter, nonlinear parameter, lower bound, upper bound. So these ones are not bounded, but there is a lower bound of 0 on the sigma parameter because that's a standard deviation. And we can see here that the source is the user as opposed to a default prior. So we can look at the stand code that BRMS created by running the stand code function, but as a warning, this is a really hard to read, not a great way to learn stand. It's really optimized for efficiency, for computers, and for the ease with which BRMS can generate the code. So the code we can write ourselves could be a lot easier to read. It wouldn't have single letter variables, and some of this could be less verbose. But regardless, this is the stand code, and if we wanted to, we could take the stand code, we could take the stand data. Stand data, this is the list that went into stand. We'll talk about pure stand code next week. And we could modify it, say if we wanted to, and refit the model. But this is how you can look at what's happening in the underlying stand code itself. So as we talked about last week, once we have fit MCMC chains, it's really important to inspect the chains for convergence. And so there are several functions in Bayes plot, starting with MCMC underscore, and we're going to use MCMC trace here, and that's going to make a trace plot, which is just that line plot that we looked at last week in slides. So here we have all our various parameters, and we have our 4 chains in 4 different colors of blue. We also have the total log prior density and the total log posterior density under LP underscore underscore. If we didn't want to include those, we could just select individual parameters with the pars argument. So I can say pars be nutrients, and I would just get that parameter. Or there's also an argument, regx pars, which lets us search for parameters using regular expression syntax. So here I might say caret, which means the beginning, and then b, so everything that starts with b underscore, or vertical sigma. And that would show me trace plots for every one of my beta coefficients or my sigma. So all the parameters here that I'm interested in, excluding everything else. And in general, this looks fantastic. We already knew the effective sample size and R hats were great, so no surprise. These trace plots also look great. There's a variety of other functions. Just to give one example, here is MCMC underscore ACF, so the autocorrelation function. In this case, it has split out the 4 chains, and then all the various parameters here are shown in the columns. We have perfect correlation with itself, and then this is one step forward in the MCMC, one leg in the MCMC chain. These all basically go right down to 0 right away, very little correlation. There's a little bit of autocorrelation in sigma and in the total log posterior. But as we talked about last week, that isn't really a problem in itself. It just means there's less information in the MCMC samples themselves than the total number of samples. So that gets reflected in the effective sample size. If you had really strong autocorrelation, you might see this going out hundreds, let's say, of lags out. You'd have strong correlation, and you might need to reparameterize your model or have more samples. So with posterior predictive checking, there's a whole bunch of functions, as we saw in the last exercise in Bayes plot, that all start with PPC, and there's this function available PPC, which gives us a list of all of the available ones. And so there's also this function ppcheck, which is built into brms, and that calls the functions in Bayes plot. So we're going to talk about there's 2 ways to get at your posterior predictive checks if you want to use the Bayes plot versions. You can also just make them yourself with ggplot or Bayes graphics, whatever you want. But Bayes plot has a lot of common posterior predictive check setups built for you. So this is going to take 50 draws from the posterior in the light blue, and it's going to plot the observed data here in dark as y and y rep. So we could have done that ourselves with Bayes plot by just extracting the response, the observations, taking 50 replicates using posterior predict on our model, and then I can pass those to Bayes plot like I was doing before to create our visualization. And the way that these 2 things interact with each other is that there's a type argument in ppcheck, and that corresponds to everything after the ppc underscore. So type equals dense overlay is the same thing as that. So doing this is the default, and that's the same as this. So in addition to that full list, there's also this ppc overview help file in Bayes plot, and it's helpful mostly in that it groups all the plotting functions together. So if you want any kind of a posterior predictive check that is a scatter plot, for example, I can click here, and those are all of your scatter plot ones grouped together. And any one of these, if I were to take the stuff after ppc underscore and put that into ppcheck with brms, then I would have the same posterior predictive check using the ppcheck function. So here I've just chosen to use pp check. I think in reality I probably actually these days would tend to use the Bayes plot function itself. But let's look at some examples of types of plots we could make. Probably far more variety than I would normally make, but it's good to see the types of things that are available. So here we have histograms. So the first panel here are the observations, the rest are replicates. The distribution of our observations and simulated observations. There's a scatter plot here where on the y-axis I've got my observations, and then I've got observations minus the replicate on the x-axis, and so on. There's a variety of types here. This is an empirical cumulative distribution function, ECDF. So you see how the distribution accumulates and whether or not they overlap each other. Here they do. These ones are probably particularly useful in this case. Let's look at this one here. So I've got my predictor x on the x-axis. On the y-axis, I have y or y rep. So this is log of the mass change and log of the mass change replicate. And they've been turned into dots and line segments. If I just do it by order, maybe it's easier to see. This one here. So that's just the order. On the x-axis, the order they were in the data frame. So that splits out the nutrients and no nutrients. So we can see here the observations versus the distribution of the simulations. And I assume these are 50% and 90 or 95%, but we would expect the observations to then be in those quantiles with the expected probability. And here they're largely overlapping. There's really nothing that's outside of the full distribution of the simulated values. It looks pretty good to me. So we already looked at this one, which was an MCMC trace. There's all sorts of available other MCMC plotting functions within brms, which I can get with that function available MCMC. If we look at some examples here, again, I've carried in that regular expression of pars, because if I didn't, I'm also going to get my log prior and log posterior density, which just messes up the scale, the x-axis of my parameters. So I'm going to tell it that I want everything that starts with b underscore or sigma. And I get, this is the areas plot. So I've got a density plot plus some interval. And if we look at the help, it should describe, I think it's 0.5 and 0.9 intervals. That's what I was looking for there, that are shaded. We can also do that with dot and line plots. Or we can use this combo plot that includes a trace plot and a density, or MCMC area ridges to make sort of a half violin or a mountain style plot. So there's lots of options there. So I'm going to save this here, and we're going to go back to plot the original data and just talk for a second about what each of these coefficients means. So I'm going to plot the data here at the beginning. So let's think for a second about what each of these means. So b-intercept, so this is our intercept value here. This is our expected value when all of our predictors are at 0. So in this case, that also corresponds to a mean pH because we centered it. So that also improves the interpretation of our intercept. And our nutrient needs to be at 0, so there's no added nutrient, so red. So that's basically the expected value here. And in particular, I should log this y, because that's what we were fitting. So it should be somewhere up there. So that's something like 1.5, and that's roughly what the mean of our posterior on the intercept is. So that's great. Then we have pH scaled. And this is the overall slope. So is our data sort of overall sloped up or down or flat? And here that's just slightly negative mean, but the posterior really overlaps 0 quite a bit. And that makes sense because we don't really see any overall slope in our data. Then we see pH squared, which is this one here. So this is our happy or frowny face shape. In this case, it's quite negative, and that makes sense. So it means we have a strongly negative or frowny face to our data that we fit. And then one of our parameters of interest, which is this nutrient. So when nutrients are added, we have a smaller increase in sea hair mass in this case. And so that is shifting down our curve by that much. And then this is our observation error standard deviation in this log scale. Okay, so now we've looked at what the parameters mean. So let's make some visualizations of the output in various ways. So one thing I'm going to do is extract my parameters here in a data frame. So if I just use as.dataframe on my fit and I just wrap it in as table so it prints more nicely here, but that's absolutely not necessary. You would have just print it out like that. Now I get a data frame that looks like this, and each one of my columns is a parameter, or sometimes a derived quantity here, like the log prior density and the log posterior density. And then each row is an MCMC sample. So if I look at the number of rows, I get 4,000, which is 1,000 times 4 chains. And that's after warm-up. The warm-up has been discarded for us, as it should. Now I'm going to make a visualization of the prior that I fit, and I could sample from the prior, and we're going to see an example of that later. But in this first example, I'm going to actually draw what the prior density is. And to do that, I'm just going to create a sequence of values from -10 to 10, because that's just where I'm going to plot of 300. And I'm going to calculate d-norm, so the normal density of those values with a mean of 0 and a standard deviation of 3, which is the prior, I believe. So that creates a data frame, and then we can plot that with our posterior. So here I am plotting that quadratic term on pH, and the histogram here is the posterior, and then the prior here is shown in blue. And I'm doing that as kind of a trick where you can use geom ribbon with my data frame. The x is the pH that goes on the x-axis, and then the upper boundary of the ribbon is density that I calculated right here, and then the y min on my ribbon is always 0, so that creates this ribbon that looks like this density with a bit of transparency. So that's an example of how I can overlay the posterior and prior. Make sure there's not a major disagreement between the two. So there's this wonderful package called ShinyStan, and you can use this with any stand model, including BRMS models. So if I just launch ShinyStan with launch ShinyStan on my fit, I will get this Shiny app here. And there are a variety of tabs you can look through, diagnosing information on R hat and F. You can have various filters to find parameters that are giving you problems, look at autocorrelation. You can click through and actually run posterior predictive checks by selecting objects from your global environment, looking at which parameters you want to work with, looking at trace plots and so on. There's some information on the Hamiltonian dynamics if you need to look into that. There's various ways that you can summarize here or explore, say, variables plotted against each other and so on. So there's lots of stuff in here. It can be useful if you've got really complicated models and you need like a graphic way of digging through your parameters and finding problems. So know that it's there, and if this is helpful to you, it's there for you. I'm going to exit that to come back. And now we're going to look at various ways of plotting the predictions from our model. So to do that, first I'm going to create a new data frame that I'm going to predict with across a sequence of pH scaled values that go all the way from the minimum to the maximum value. 500, this could be 300 or whatever, but a big enough number that we have a smooth curve, and then 2 levels of nutrients. The expand.grid function just creates all combinations of the things that I give it in a data frame. So if we look at the tail of new data, we have nutrients of 1. It starts off with nutrients of 0. And then we can predict from this in various ways. So we're going to use the posterior EPRED for the expected predicted value. This is effectively what you're used to seeing if you've used GLM or linear LM for linear regression. We're going to feed it the new data. And we'll plot this out in a second. But the important thing is it comes back with 4,000 rows and 1,000 columns. So those 1,000 correspond to the number of rows of new data, and the 4,000 correspond to all the MCMC samples. So for every one of our new data that we want to predict on, we end up with 4,000 samples that we can plot or visualize however we want. So I'm going to summarize them by their median and their interquartile range, so their 25th and 75th probability quantile. To do that, I can use the apply function. The apply function in the second argument is the margin, and the margin is 1 for row or 2 for column in this case. And then the third function is the function that I want. The third argument is the function I want to apply. Here the median, here the quantile, and because of the ... which get passed on to the function, I can pass the probability argument. So if we look at quantile, there's a probs argument. So this gets passed on to quantile, so I want the 25th and the 75th quantile. Then I'm going to do the same thing, but I'm going to do it on posterior predictions, which you remember, Bayesians like to think about predicting new observations. So posterior predict creates new observation predictions. So it adds on the observation error. So I'm going to do that, and I'm also going to calculate the 50% credible interval based on quantiles, and then I'm going to plot it. So I'm plotting my data as geom point, and then I've got a ribbon for the upper and lower expected values, which is the inner ribbon here, and then I've got a ribbon for the new observations, which is the outer ribbon here. And so there's a lot more uncertainty in our predictions of new observations than the uncertainty on the mean, the expectation itself, as we would expect. So this inner one is what you're probably used to seeing with LM. With LM in R, there's also a prediction interval, they call it, and that would be equivalent to this, although LM, I believe, uses a plugin, as they would call it, estimator. So it's not including both uncertainty in the expectation and the observation error at the same time. So this is fully incorporating all uncertainty for new observations here. So now I wanted to talk about ways that we can summarize the posterior distribution of parameters that you might report on from the model. So as before, I can make a data frame, which is an easy thing to work with here, of all of my parameters. The rows are the MCMC samples. I'm just going to extract this squared, this pH squared coefficient, and call it pH2 samples for ease of coding. And if I look at how many of those are below, the proportion of those that are below 0, that gives me the probability of the frowny face. So probability this is a downward curve thing versus the probability this is an upward curve thing, which is very small. And like we talked about last week, this works just because that creates a bunch of zeros and ones, which get treated as trues and falses. They get treated as ones and zeros in R. And so the mean of that is equivalent to taking how many of them are ones and dividing by the length. It's just faster. So we could also ask, what's the probability that the change in sea hair mass is greater in the case where nutrients were not added? And the answer is very high probability, 0.99 probability. So that's saying what's the probability that the red here is above the blue here. But once we have these MCMC samples, we can do lots of things with them. We're not limited by simple questions like this. We can ask more complicated questions, and we can fully quantify the uncertainty and report a probability for that comparison. So I'm going to make an example here. It may seem a little bit contrived, but it's just an example of what we could do. So what I'm going to do is I want to ask, based on the expected values, is it here at lowest pH with no nutrients, how does that compare to here with average pH with nutrients? So I basically want to compare the distribution here to the distribution here. There's lots of ways we could do that. I'm going to do it here using that posterior EPRED or posterior LinPRED, which will give you the same thing here because these are a linear regression. This would give you a different answer, I believe, if this was a generalized linear model with a length function. Here they're the same thing. They're giving us the expected value. So I'm going to create a data frame. And this data frame is really simple. It just has the minimum pH and a nutrient of 0. And I'm going to make a posterior prediction at that. If I just ran this, I would end up with a matrix with one column, but I want this to be a vector just to make it easier to work with. So I'm going to extract the first column. Then I'm going to do the same thing for the mean pH with nutrients. So condition 2 is another simple data frame. I'm going to save those. And because these both, the MCMC chains line up between these two vectors that I've created of PP1 and PP2, I can add, subtract, multiply, divide them by each other, and they account for all the correlation between them. So in this case, I'm going to exponentiate them to take back out of log space and then divide them. So I'm asking for the ratio between these two in natural space. And I can plot that out. I just put a line here at 1. So this is the posterior distribution on the ratio of this second comparison to this second condition to this first condition. And we could, for example, take credible intervals, quantiles on that, or we could calculate how much of this is above 1 or how much of this is above 1.5. So we can quantify that ratio with fully taking into account all the uncertainty. Okay, let's open up the file. Okay, let's open up the file 07 priors-brms.rmd. We're going to talk about some particular aspects of how priors are treated in BRMS, specifically around intercepts. So we're going to start by loading some packages, setting up our caching for BRMS, and then we're going to simulate some really simple data. We have some predictor that goes from 1 to 20, a slope of 0.3, an intercept of 0.2. We have some observation error. And with that, we've created a data frame with a predictor X and 8 observations of Y. We can plot that here. So if we wanted to fit a simple linear regression of Y on X, we could find the default priors for the parameters with this function default_prior. And we see something like what we looked at before, but now we don't have to fit the model in order to figure out what we need to supply. So we can look here and see that we need to supply class B, which is going to be for our predictor X. We have an intercept that we can specify, and the default prior actually has a mean that is not 0. I believe it's based on a mean-centered version of the data. And then we have a half student t prior with a degrees of freedom of 3 and a scale of 2.5 on the standard deviation of the observation error. So if we fit our model, we could fit our model with the default priors like this, but instead we want to specify the priors ourselves. Now if we fit it like this, as we did before, so we've got y tilde x as our formula, we have our data and our family, and we set our priors here, and they match the priors in our available priors that we saw with default prior. We have turned on sample prior equals yes, so that we will have samples from the prior that we can work with. We'll have to wait for a second for this to compile. So that's one way we can set it up. And the other way we can set it up is what we have here with 0 plus capital I intercept. So for BRMS, this is a special formula syntax, and it treats this now as an intercept, and this suppresses the default intercept in an R formula. This could also be -1. It would do the same thing. So I'm going to fit this model. It also has to compile. And then we'll compare the two afterwards. These both have a normal prior of 0, 5, standard deviation of 5 on the intercept, a standard normal prior on the slope coefficient, and a student t degrees of freedom 3, scale of 3, half t on sigma. So if we look at these two models, this first one, model 1, if we look up here at transformed data, what it's done is it's actually mean-centered all the predictors first before fitting the model, which is going to affect the interpretation of the intercept. The intercept is now the expected value at the mean of the predictors, instead of when all the predictors that we gave it are equal to 0. And then it back transforms the intercept here in the generated quantities. We'll talk more about these sections of the stand model next week, into something called B underscore intercept. If, on the other hand, we looked at stand code for model 2, we have a simpler model. There's no transformed data. Our intercept is just part of the vector of B coefficients. And there's no generated quantities that rescales the intercept for the output. So let's look at what that gives us. So I can take the posterior of all the parameters with as draws df. That's the same thing, doing the same thing here as as.dataframe. So if we look at sims1, each of these is a parameter, and then each row is a sample from the posterior. So if we look at the mean of intercept in model 1, it's 3.334. And if we look back at the data that we gave it, that should be the expected value of y at a mean value of x, which should be 10 in this case. So that's what we see here. But the intercept as we gave it would be when x is equal to 0, which would be over here. And so that's the back transformed version. That's the B underscore intercept. On the other hand, if we look at model 2, the mean of the intercept is approximately what we would expect over here with an x value going in of 0. So it's now, as we have specified the model, is how it comes out. So I would suggest that, personally at least, I prefer to specify the intercept explicitly so I know what is happening in the model. And I often would mean center the predictors going in such that this intercept would represent the expected value at the mean of the predictors, but I explicitly know what's going into the model as opposed to having to come up with an intercept on a scaled version of my predictors. The way it's done like this in BRMS is to make it more robust to people not thinking about the prior on their intercept. So it makes the scale of that more generally applicable to a normal prior. You don't have to think as much about it, but if you're willing to center your data first and you want to know what's going on, I would suggest explicitly specifying the intercept. So now we can take prior draws from our model because we said sample prior equals yes. And that's just one way that we could visualize the prior. So that's the standard normal prior on the predictor x, the coefficient associated with the predictor x, and that's the half student t prior on sigma. So if we want to do a prior predictive check, one way we can do that is to say sample from the prior only instead of yes. So I'm going to run that, And now, if we look at the model code, we can see that there is a logical argument in the model that says only include the data likelihood here if this argument prior only is false. So when prior only is true, which is what happens when we specify this here, the data likelihood does not get included. And so we're only looking at draws from the prior. Then we can get expected values, so push forward prior predictive simulations using the posterior EPRED. Despite the fact it says posterior, there's no data going into our likelihood, so this is only the prior. So this is a prior push forward simulation, and this is a prior predictive simulation by using posterior predict, so this has observation error included. And now if we just take 3 example replicates from the push forward simulation, we can see what those look like here. They are straight lines because these are basically possible regression lines and they don't have any observation on them. And if we look at the prior predictive simulations, there's lots of noise here because we're adding observation error on top of the draws from the slope and intercept coefficients. So we had weakly informative priors in that previous model. If instead I had much more vague priors, so here I've increased the standard deviation to 100. And I've increased the scale on the standard deviation of the observation error to 100. And now we can take posterior predictive, so prior predictive simulations. And then I'm going to take draws from 1, 18, and 42, so just some random simulation draws. Plot them out. You'll see that I have a much larger scale on the y-axis. This has been, the intercept is quite negative, and then the slope is quite negative. And here I have very, very positive slope. So these are very different in scale from the observed data. In reality, this would be some applied problem. We would know something about the domain that we're working. We might know that these are completely impossible values, in which case we would not call these weakly informative priors.